Okay, so welcome to the fourth session of the Olas Dev Academy 5. As ever, we'll just start with a quick disclaimer. So this session is organized by Valory to educate people about Olas and developing autonomous services. Valory is one of the core contributors to the ecosystem, the Olas ecosystem, and all content that we provide here is an expression of our view and does not constitute financial advice. Firstly, the emphasis of today's session is the Open Autonomy framework. Open Autonomy is the open source stack that largely Valory has pushed forward, and essentially it's what you use to develop autonomous agents and services in the ecosystem. It won't be the only framework or that emerges in the ecosystem, and the protocol has not been architected certainly to only support one framework, but it is currently the one which is the most heavily used. So I'll hand over to Jose.
Thank you, Oak. So let me try. So again, just leave me briefly present in case you were not present in the last session. So I'm Jose. I'm also working with Valory, and I work in the research department, and I will be guiding you through these first steps through the Open Autonomy framework, which is the framework, as Oak mentioned, to create autonomous services. So this is the agenda for today. So we will briefly recap what is an autonomous service, so what are the main components in a little bit more detail than in the previous session. What are the steps to create an autonomous service? And then we will I will guide you through a concrete example, which is a demo service that we have, which is the Hello World service, which hopefully will be didactic enough so that it can give you some background and confidence so that you can start exploring, understanding, and start modifying the source code of an existing service. So this will be done on the lab session. And finally, we will have some time for providing you some, let's say, exercise or homework in case you have time to do it, and some questions at the end. So, okay, so what is an autonomous service? So it is essentially a service that runs off-chain, as we already know. It enables complex processing, takes action on its own, and it's crypto native by construction. It is a decentralized, trust minimized, transparent, and robust. And the Open Autonomy framework is the framework that enables building these kind of services. So as you already know from the previous session, so an agent service, an autonomous service is composed by a number of agent instances. So each of these instances derive from one or multiple canonical agent. So let's say a canonical agent is, we can say it's the source code of the agent, and the agent instance is the actual program which is executing this source code. So that's the terminology we are using here. So each agent is controlled by an operator. So the operator is the party that provides the infrastructure to run these agents. So an operator is also in charge of running what we call the consensus gadget node for each agent instance. So the consensus gadget is let's say the part of the autonomous service that is in charge of the consensus layer among the different agents that compose the service. So this is something which the framework completely abstracts away from the programmer. So the framework gives you this feature, so the programmer doesn't need to take care of ensuring the, let's say, the consensus among the different agents. So let me switch to the next slide. I will go back to this again. So this is what I was referring. So currently this is being implemented as Tendermint nodes. So the operator runs the agent and the consensus node. And the consensus gadget nodes they are connected to the consensus gadget network. So as I said before, the canonical agents versus agent instances. So the canonical agent is the source code. The agent instance is the actual program that it's running on an operator infrastructure. So it can be the case that a certain service has different canonical agents. But for this example that we are using in the Academy, each agent instance is implemented through the same base, so through the same canonical agent. However, these canonical agents can be parameterized accordingly. So, for example, I can assign that one agent has to collect information from a given URL, and another agent can collect information from another URL. And finally, the last component that I want to mention about what constitutes an autonomous service is the FSM app. So the FSM app is a component that is inside the canonical agent. So let me switch back again to this diagram. So the FSM app is actually the core component that executes the business logic of the service. So this is actually where the programmer needs to put the effort when they are defining an autonomous service. So they need to define this FSM app, and this will be like most of the part that we will be devoting this presentation today. So what are the steps to define an autonomous service? So essentially, we need to follow these steps. So, I mean, of course, among each of those steps, there are like a complex process, especially on the second one. So the first one is define the finite state machine that defines the service. So autonomous services are defined through a finite state machine. So this means that we need to split the service functionality into a collection of states and define what happens in each of these states, whether it's collecting information, whether it's just making some computation, whatever. So we need to split the business logic of our service in the form of a finite state machine. So, so as I said, the finite state machine is composed of different states, and each state, after executing the action associated to each state, so the state of the service changes, and this is represented by casting an event. So this event is what we will transition the current state to another state, and then the finite state machine will execute the operation of this state, of the next state. So this is like on high level how this should be defined. So we need to define the states and what are the transitions from each state. So the next step, when we have, let's say, drafted how we are going to split the business logic into a finite state machine, is code this FSM machine into what we call the FSM app of the service. And when we are coding this FSM app, we will define what are those states, what are the action. We will code concretely what is the action that it's doing the agent, and we also need to code these transitions and how these transitions are going to be related per state. Let's say if I'm in a given state, I receive one event, so I move to another state. So finally, we need to code or define the agent that contains the FSM app. So the framework is designed so that it's extensible. So usually this part, it's basically defining what are the components that made this agent. So one of the components will be, of course, this FSM app that defines the business logic, but the agent can have all the components. Like, for example, if it's interacting with an HTTP server, it will have a component that allows to execute HTTP calls to API. Or, for example, it can have another component that allows to connect or, let's say, send transactions to a blockchain. So it will be a ledger connection in this case. And finally, once we have made all this coding, So what it remains is deploy and run our service, which, by the way, this is what we did in the previous session with the trader. So we already have some experience on this step here. So if we go to the first part here, define the FSM that define the service. So as I mentioned, so this it reduces to identify the steps and identify the transitions that that define the next action when we are in a state and something has occurred. So these transitions can be like normal transitions, what we call the happy path, which is, let's say, the expected behavior of the service. But you also need to account for error transitions. Let's say if I'm making a call to an API, I don't receive an answer. How do I handle this error? So I need to somehow cast an event that represents this error. And also we need to take into account timeout transitions so that the service doesn't get stuck in a given state. So once we have, let's say, in pen and paper how this FSM is designed, so the next step is define the FSM app, let's say code the FSM app itself. So, and this is possibly let's say, the part that we need to devote most time when defining a service. So the framework is designed so that for each state of this FSM, of this finite state machine, we need to define a number of components or classes. So in particular, we need to define one behavior, one class which is called behavior, one class that is called round, and we need one pair of these classes per state. So the behavior class of the FSM app is executing the proactive action. Let's say it's sending on some transaction on chain, it's contacting an API, it's executing some local computation, whatever. So this is the part of the code where we need to define the action that it's going to be executed in this state of the finite state machine. The second component that we need to define are the rounds. So the rounds is the component that, let's say, understand what, let's say this way, it understand what has happened during the behavior execution, what is the status, and it casts the appropriate event following the behavior execution. So let's say this will execute the code, and this will cast the event. So once we have when we depart from this behavior, from a given behavior, and the rounds cast a given event, so we know how to transit to the next behavior that will execute the next action. So this is defined in the ABCI app, so which is another component we need to define. So this component here is essentially defining the transition function of the finite state machine. So we will take a look at this afterwards. So I know it's a lot of information and components, but we will see this in an example later. So again, so this is essentially a class that defines what are the transitions when we are in a behavior and the round casts a certain event. So the round behavior, it's another class. So this is not very difficult to code. This is just, let's say that way, it's kind of boilerplate code. So it's the class that is in charge of gathering the ABCI app and executing it. So another component that is part of the FSM app are the payloads. So the payloads is the information that gets exchanged by the nodes through the consensus gadget. So for example, if in a certain state of my finite state machine, I need to share the information I have collected from an API, so I will do so through a payload. So so whenever I transit from one round to another round, so the design of the framework requires that we need to have a payload. If we don't need to, let's say, send any relevant information, which I mean, I think this is not very common, but if we don't want to send anything, we can simply send some fixed value or something like this. But this is the content that will allow to share information between the different states. So as I said, so there are other components like the connections. As I mentioned, if I want an HTTP connection, if I want a ledger connection to make transactions on-chain, protocols, and so on. But I'm not going to go into detail of this because it will be like a little bit overwhelming for a first approach of the framework. But just to let you know that that we also require other components to define a service. So the next step, once we have coded this FSM app, it's code the agent that contains this FSM app. So we need to configure the agent.yaml. I think there was a question about this in the chat. So the agent.yaml is just a configuration file where we define what are the components that will define this agent, the FSM app, the connections, and any other component we want to add here. So we will examine how one of those files look like afterwards. So it is recommended that we execute end-to-end tests. We will show you some examples also on the repository that we are going to share with you. And other unit tests. So this is not mandatory, but it's highly recommended that that you perform this kind of tests before having a service in production. Finally, we need to configure the service.yaml, which it's also a wrapper file. It defines, let's say, how many agents compose the service. And it has also another number of configuration parameters. So for example, if I want to parameterize different variables for agents, so I will do this on the service.yaml file. And this is pretty much essentially. So this is the 4-step process. Define the FSM, that's pen and paper. Code the FSM app, which is what I will show you an example today about this. And finally, code the required configuration files, the agent.yaml, the service.yaml, and so on. And finally, deploy the service. So in order to show you some example on how this is implemented, so we have this simple service, which is called the Hello World service. It's extremely simple. It has only 4 states. Just to get an idea, so the trader agent that you were running on the previous session has, I think, of the order of 20 states or even more. So for this reason, I'm telling this Hello World is very, very simple. So it's just for demo purposes, and it's not secured in the Olas protocol. And the reason for this is that this service doesn't execute on-chain actions. It's just to show you how the framework works, how to integrate the components, and so on. So this is how the Hello World service looks like. So this image should be already familiar to you. So we have the service in which we have a number of operators. Each operator runs one of those agents with a consensus gadget that execute the consensus layer. This service has connectivity to internet, and actually it's accessing the centralized randomness service, which is called drun. And I will explain why it's doing this. So if you execute this service, what will happen is that you will be executing all these 4 agents and all these consensus gadget on your same machine. So when you examine with Docker, you will see that you will have a total of 8 containers. And the reason for that, as I said, is because you will be executing, let's say, you will be these 4 operators here in this picture on your local machine. So this is how the demo works. So just following the steps that I just mentioned to define a service. So this is essentially the overview of what the service is doing. So I have a finite state machine here, and I have the states that each state represents a different action that the service is doing, and I have the transitions from one state to another state. So the first state here, what is happening is the initial state. So this is quite common for all the services. It's a registration state, which essentially means that agents are willing to participate in this service, and they share some parameters and so on. So when this when this state has finished, we we emit this event done. So this is this event is emitted by the by the corresponding round here. And we go to the next stage. So in this next stage, what happens is that agents connect to the internet, connect to this service here, and collect this decentralized randomness parameter. So all the agents should collect the same value because they are accessing at the same time, approximately. So, and I believe this value changes every 30 seconds or something like this randomness. So what happens here is they collect this randomness and they will share the value that they have collected. Once the FSM verifies that all the agents have collected the same value, so this will be marked as success. So this will be the done event, and we go to the next state. If one of the agents is malicious or something, or some agents are malicious and they don't send an honest value of what they have collected, so it's possible that we don't have this done event, and instead we have an, let's say, error event, and the finite state machine dictates that I need to transit again to the same state. So in the next stage, select keeper, what we do is to nominate one of these 4 agents here to print a message on the local console. So I will go into detail about this state afterwards. So in the next state, so if this is successful, I will print a message on screen. And that's it. That's just a print command. And once this is done, we go to another state, which is common for many services. And what is doing is just waiting a little bit and then going to the main cycle of the business logic again. And this repeats again and again. And this is the business logic of this service. So, okay, right now I am going to, let's say, make concrete how this is implemented. So we are going to examine the source code. So before proceeding, I just wanted to check, is there anything that wasn't clear until this point that you need further explanation or something?
I didn't follow what the round part was. I might have missed when you described that in detail.
Yeah. So, so as I mentioned, every state of the finite state machine needs to define 2 parts. One part is the part that executes the action. So let's say, for example, in this case, print message. So the behavior is the component that will print the message, execute the proactive action. And the round is the component that will, let's say, evaluate that everything has been correct, and it will emit this event here. When it checks that, let's say, the consensus state is as expected, it will say, okay, all the agents have executed their action that they are expected to execute. So I can emit this event because, I'm in the happy path. So let's say I emit the event done. So this is the responsibility of the round, just emitting events.
Gotcha. Thank you.
Okay, so let's examine now a little bit the source code. Okay, so we have the Hello World repository, which we will share afterwards. It's on GitHub. So let me just collect. Yeah. So here we go. So again, as I said, so this is the Hello World repository. It's on GitHub. We will let you know how to clone this repository. So, and this is what's inside this repository, and we will now take a look on how this is implemented in the framework. So the first thing I wanted to comment is when you open one repository that contains a service, so the structure that you will notice here is that it has a folder which is called packages.json. So this is the main folder where the source code is developed. So this folder has an index file here. And if we examine this index file here, we can see that what is being developed in this particular repository, it's like the Hello World skill. This is the FSM app that we will examine now, the Hello World agent, and the Hello World service. So additionally, we need some other components like protocols, connections, and so on that I will not go into detail of those ones here, but just to let you know that these components are required in order to run this particular service. So if we examine these packages, so in this case, it's on vendor Valory. Okay, so the FSM app, it's under the folder skills, and it's called Hello World ABCI. So this is the FSM app for the Hello World. So and here, let me maximize this. Can you read my screen, by the way? I don't know if it's too small or I should.
Oh, good.
Okay.
Good for me.
Okay, so if I examine here, so I have Hello World ABCI. So for historical reasons, the FSM apps end in ABCI. So whenever you see something ending in this, it's because it's an FSM app. So, but that's just a historical naming convention. So here we have a number of files. So we have behaviors, which is where we encode the behaviors, obviously. The same for rounds here. And the same for payloads. So let's first start with behaviors. So, okay, let's for the moment forget about this first state here, because I think it's simple if we start with the second state. It's more clear. So if we go to this final state machine, while now we are here on this state. So what should the service do in this state? So as I said, agents need to contact this run service, collect the randomness, and share the value that they have received from this source. So in the service, let's see how this is implemented. So the first part that we are going to see here is the behavior. So just for convention, we append behavior to the behaviors, just to be consistent with the naming conventions. And this is a class that it's derived from a helper class that we have here. So this is a class that we have just made for convenience if we want to use some common methods for our behavior. So we place them in this base class here, but this is up to you. So when we are inside this class, so all the behaviors have a parameter that needs to be set, which is the matching round. In this case, it's the collect randomness round, which we will inspect afterwards. And behaviors need to define this method, which is async act. So async act is the method where the action is executed. So if we continue reading here, so it's a lot of code, but let's examine what are the most interesting parts here. So essentially what it is doing here, so let's ignore this part for the moment. So first of all, it's reading from the configuration some API specs where, you know, the URL of this service that I want to contact is described and so on. So this is done through the configuration, through the parameter configurations. So this is kind of service parameters that I will give you some insight on how they are set up and how can you modify them. So actually, we already modified or took a look at them during the previous sessions when I show you like the configuration parameters for the trader. So what it's doing here, it's retrieving this configuration to access this server, and it's building the request, and it's executing this request. So the execution of this request, usually what, if I was writing a script or something, I would import the requests library and, call get or post or whatever using this library. In this case, the framework requires that these requests are done through this method, which this method is using the components of the framework. In this case, it's using an HTTP connection. And this is the the way the framework is designed to be programmed. So when I need to execute an HTTP connection, I do through this method, which it will take into account to redirect to the proper component of the agent. So I get the response from this HTTP request, and then here it's just code for parsing this this observation that I have received. I prepare the payload, and in this payload, as I mentioned, the payload is a data class that contains the information I want to share. I simply place the collected information from this API call that I just made. So finally, the async act method, needs to send this payload to the consensus layer. This is done using the send A2A transaction. It has to wait until the round has ended, and finally it has to mark as done. So these 3 lines here, they are common for all the behaviors that you will need to program. So this is part of the framework. So in summary, we are contacting the HTTP service. Well, the API service, in this case, the different service. We are collecting the output, and we are sending what we have received as a payload. If you want to see how this payload class looks like, so it's very simple. In this case, this is the payload that I am using. It just has one string, which is the randomness here. Okay, so now let's go to the other part, to the counterpart of this collect randomness behavior, which will be the collect randomness round. And let's see here, and surprise, because it has almost no code, this class that I have defined here, and I will explain why is this the case. So this class here is, as I mentioned, it's in charge of understanding what has happened on the behavior side and emit the necessary event. So in this particular case, all the agents need to collect the same randomness behavior. So when this is the case, what we do at the framework level is we make that this class here inherits from a base class, which is provided by the framework, which is called collect same until threshold. So this class here is designed to wait for all agents to collect the same information until a threshold of agents has, let's say, provided the same information. I need to define a number of parameters here. The payload class, which is the class that I saw before. The synchronized data class. I will explain what this is later. And the done event. So the done event here means the event when everything has gone okay. This base class will be in charge of casting this event done. If I haven't reached the majority, I need to define what is the event in case the majority hasn't been reached, and I will cast this event here. Okay. So so essentially I don't have to program anything. So the framework will take charge of doing this. So there are some other parameters I need to define, but I mean, I'm not going to go into detail of all of them at this point. So let's say there's another round, for example, here, that it's select keeper. If you remember, in this select keeper, what happens is that all agents have to nominate a given agent to print a message. And finally, I have this print message round, which I have a little bit more of code here. And the reason for that is because while in these previous rounds, I have enough with the let's say, functionality that the framework-based class provides. In this class here, I need to do like a little bit more of work, and this is why I need to overload this end block method from the base class. Okay, so let's go to this class, to the select keeper. I want to explain something about this. If we go to the behavior, in this case, again, the behavior is where the action takes place. So in this case, I need to compute locally the index of one of the agents, or the address of one of the agents. If you examine this class here, again, I go to the async act method, which is where the action takes part. You will notice here that I'm using something random here. And this is something very important to notice. So agent services have to be defined or thought with a deterministic mindset. Let's say everything what happens on a round or on a state has to be deterministic, meaning that all the agents should be able to derive everything, the same information. In this case, all the agents should be able to randomly select the same agent. So how do I do this? Well, in the previous state, I collected some randomness from a decentralized source. So I can initialize all the agents with this seed using this randomness that I collected from the previous source in this state here of collect randomness. And then everything that happens here will be deterministic. So all the agents will, let's say, select the same address as the keeper. So you can see here that this agent here, if you examine the code, here I have selected the keeper address. What I'm doing here is I'm creating a payload where I send the keeper address that I have selected. If all the agents behave honestly, they will execute this code here deterministically, and they will all agree on a same nominate agent. So this is important whenever we want to execute some actions that can only be executed by one agent. Like, for example, sending or signing a transaction on-chain. So if I go to the round of the select keeper, again, it's the same as the previous one, collect same until threshold. So here it's very similar to what happened if everything has gone well. So I will go to the next state. If not, so I have these transitions that go again to another state. So finally, in this file, what I wanted to share with you is the ABC app class, which is the class that defines the transitions. So this is very easy to understand. So the important point here is this transition function here. So this means that if I'm in the transition round, in the registration round, and I receive the event done, I transit to the next round, to the collect randomness now. So this is exactly what's happening here. So for example, this one, if I'm on the select keeper round, I receive this event, I transit to print message round, and so on and so forth. So this is essentially defining the wiring of this finite state machine here. So there are just a couple of things I wanted to mention before we go to the question. So again, I'm running out of time. I'm sorry for that. So we talk about something which is called the synchronized data. So this is also on the rounds.py file. Okay. So the synchronized data is, let's say, a synchronized storage. So it's a storage that it's common for all the agents. So this means so that all the agents have the same value for any variable that I want to store here. So this is automatically done through the consensus layer. So the programmer doesn't need to do anything special here, just ensure that I'm passing the correct information to on the payloads, and that the rounds process this properly. And this synchronized data will be updated automatically. So for example, in this case, let me see. in the collect randomness round. So there's an event. So sorry, there's a payload which is collect randomness payload, which if I go to collect randomness payload here, I have this payload which is randomness, and this is processed by the round, and it's updated on the synchronized data class. The last thing I wanted to mention, it's about the configuration parameters. So we commented about this when we talk about, let me see, when we contact here, when we have these API specs, or we have, for example, on the print message behavior. So yeah, so we have here some parameters. So it's reading parameters, a parameter that is called hello world string. So how this is implemented. So I need to go to the configuration of the skill.yaml. Okay, so I have here, let me find. Here I have defined a parameter which is called hello world message. Okay. So how can I access this parameter from the behavior here? So I need to define the parameter class. So this is on models.py. And here I have to define this value. Let me see. Yes, here I need to define hello world params value. So you will notice that I have this variable here, which reads from the configuration, which is this hello world message parameter. And once I have coded this, then I can access the configuration parameter from the behavior. So that's everything so far. I know there's a lot of information, so you're welcome to ask questions here after we finish the session, or even in the Discord. So, but before, just wanted to briefly show you about the agent configuration file and the service configuration file. So as you can see, if I go to agents, hello world in the repository, so I have this config.yaml, which is the file that defines the agent. So there's a lot of parameters here. Obviously, I'm not going to detail all of them, but I just wanted to see. I just wanted to mention here that this is this agent is loading this hello world ABCI FSM app that we have. We just took a look at it, which is of type skill, component type skill. And here I have under parameters, arguments, I have this hello world message that I can change at the level of parameter. If we go to the service side, finally, so that's the last file I'm going to share. If we go to the service, it's also a configuration file. It's where the parameters for the different agents can be specified. So for example, this means that for the first agent, I can specify one hello world message. For the second agent, I can specify another hello world message, different, if you notice here. So they have different strings. And this is what I can do in the service .yaml, which is the configuration file. So next, how can we run this service? Just very quickly, I just wanted to show you how to run this service. So you can find the instructions on the Autonomy developer documentation. So it's on the guides. Let me share with you. If you go to docs.autonolas.network, you have one quick start guide. So here, this will guide you on how to run this hello world service locally. So I just have here a convenience script that will execute. Execute these steps to run this service for me, just to be quick in this presentation. The process is very similar to what happened when we wanted to deploy or to execute the trader service. So it's essentially downloading the source code, building the image, and now it's launching the Docker containers. So as I mentioned, so this service will be launching a total of 8 Docker containers. Now it's launching the ABCI, which is the agents themselves. And after this, it's going to launch the Tendermint nodes, which will execute the consensus layer. Let me just copy. Well, it takes a while, a few seconds. So let's see if it's going fast. Okay, here we go. Okay, now the service is running. So as you can see here, maybe it's a bit difficult to see because its lines are very long, but there's a total of 8 Docker containers. So you can examine the logs, as you usually do for Docker containers here. Let me paste one useful command line, which will actually show you. So this service in action. So let's see if it. So here we go. So this is from the logs for the different agents. So as you can see, we have 4 agents in total. So they are the different colors here, 0, 1, 2, and 3. And we have seen here that only one of them has said hello world. So the other one have this sad face here. But there's only one agent that has mentioned hello world. So you can see how this is executed if you examine, let's say, the print message. You will see that there's an if, a conditional statement, which says, if I'm the nominated agent, print the hello world message. If I'm not the nominated agent, print just this face here. And that's everything. So the service will continue cycling and so on. So I think, again, I have been over time. I'm sorry for that. But I think I have finished commenting everything I wanted to say here. Just we have prepared a couple of exercises. So I believe we are going to share these slides with you. In the first exercise, we ask you to add a new parameter to the hello world service and print this parameter on screen. And on the second exercise, we ask you to store a new value on this synchronized data that we just commented and print this value. And I think that's pretty much everything from my side. Of course, if you have issues like doing this homework, so we have this dev help channel on Discord. So you are more than welcome to send your questions there.
So yeah, with that, I just want to say thank you to Jose again for another great and very clear presentation. Obviously, it's a lot to get through in a short space of time, but I think it was very clear. So thank you again to Jose. Yeah, as I say, I'm going to drop off, but depending on whether or not you have questions and Jose and Adriano have time, then do stay on and ask them. But otherwise, thanks very much, everybody, and see you on Wednesday.